All right, I think we're going to start. All right, thank you for coming. My name's TJ Bay. I'm one of the co-organizers, along with Chester here. I'm a data scientist at Ask Media Group. And so I'm very interested in this talk because I'd like to be able to do AutoML. That would be amazing. So I want to get a little introduction to what people are doing out there. Let me see. First of all, I want to thank AppDynamics. So they're our host today. They very generously provided all of the food, drinks, all of the AV, as well as the space. So thank you guys. And of course, they're hiring. So I've been told there are some recruiters here. So if recruiters raise their hands, if you're looking for jobs, find those people. I see one over there too. Okay, thank you. All right, well, we have 3 talks, so let me just get right down to it. Actually, let me take that statement back. Let me just briefly mention an upcoming talk. So it has not officially been announced yet because we're still trying to nail down some of the speakers. But on April 10th, we're going to have a talk along with Google's offices in San Francisco. It's going to be another sort of machine learning focused series of talks. So the first one is going to be about Airbnb's machine learning pipeline, something similar from Lyft, and then probably a talk from Google. We'll see. Okay, let me go ahead and introduce the first speaker. His name is Yifeng Liu. He is a staff engineer from the Google Brain team, and he is the tech lead of Google's AutoML product that he's going to tell us about. So let's thank our speaker.
Thank you, everyone. My name is Yifeng. I'm from Google Brain team. We have an AutoML team under Google Brain. So I also tech lead Google's first AutoML product, Google Cloud AutoML Vision. And after that, I'm working on some other AutoML efforts. Our goal is to try to make machine learning more scalable and democratize AI for everyone. So let's get started. Before the talk, I want to ask you a question. What is the bottleneck of the broad application of machine learning in the real world? Like Google already say AI first for 2 years, but till now, there's still a lot of domains that machine learning haven't been fully touched, or it's hard to touch. So we want to ask these questions. And this question leads us to the motivation why we propose the AutoML this term. We can see machine learning as 3 essential factors combined together and make a machine learning solution. One is a machine expert, like everyone here. You are the most valuable dimension for this formula. And then we need the data, and then we need the computation. With that, we have a machine learning solution. So we want to evaluate one by one to see which one is the bottleneck for the more AI applications. Is the data bottleneck? We don't think so, because these days, like every business embracing digitalization, and you can very easily to get a very affordable big data and cloud services. So everyone could put all their data on cloud and process it. So I guess most of the company suffer from the excessive data problems. Like you have a lot of data, but you don't know how to mine the revenue from it. That's a problem. Is computation the bottleneck? We also don't think so. This is research from OpenAI. Based on their research from 2012 to 2018, the AI computation is doubled every 3.5 months. Everyone knows that the Moore's law is like every 18 months, but this one, the AI computation is increased credibly, like double every 3.5 months. And since 2012, it already increased 200,000 times. This is based on the evaluation from the 2012. There's a net named AlexNet, which wins the ImageNet of that year. And based on the computation of that year to the AlphaGo, which is happened in early 2018, the computation needed to train such kind of model is increased 300,000 times. So, and this trend seems still going because we see that NVIDIA's GPU and Google's TPU iterate very fast, and both companies believe that this trend can still be kept. So we think machine learning expertise is the bottleneck. So based on the linking and Indeed investigation, the machine learning is a very scarce resource globally, and the supply and the demand gap are huge and become bigger and bigger. So congratulations, everyone here are scarce resources globally. So that's a good thing. But from Google's perspective, we don't want to see this happen. We want to see machine learning could help the world. We want to see it everywhere to improve the efficiency of the business. So how could we solve this bottleneck of the human? This is another quote from Yosha Bengio, which is a very famous machine learning professor. He backs up the idea that if we want to train a new machine learning expert, it takes a lot of years. So we already see the gap become bigger and bigger, but we don't have time to train a new one to minimize the gap. So based on this analysis, we want to change this formula a little bit. The new formula is look like, we are thinking like, could we try to materialize machine learning experts' domain knowledge, your expertise? We try to use an algorithm to materialize that. We call it AutoML. With the same data, and about those domain knowledge or heuristic that we very hard to be materialized as algorithm, we give them 100x more computation, because we already see that the computation capability is increased exponentially. So we believe that this is, even the computation is not available right now, it could be available just in 3 or half a year. So could we, based on this new formula, to solve the same machine learning solution, machine learning problems, the same good or even better? This is why we proposed the AutoML. It's not be proposed alone, but with more computation. And we can compare the AutoML and the traditional ML. What's the difference? In the machine ML context, the number of the machine learning applications are limited by the availability of the machine learning experts. Saying, for example, if there are 1 million data scientists in the world, then we can only solve 1 million tasks globally. That's a minimum. That's a maximum, sorry. But if we talking about AutoML, we want the bottleneck shift from the human to the computation, saying, meaning that as far as we can build more computation, we can solve more machine learning problems. So the bottleneck is changed from human to the computation. And we think this is a better way, or this way can scale better than we scale human. So with AutoML, the machine learning application could scale with computation. This is the goal of the AutoML. So someone asked me that when you have an AutoML, whether our machine learning expert or data scientist will lose a job. This is totally wrong, because AutoML is not a zero-sum game with data scientists, but it's a win-win solution for the whole society. AutoML is not to try to replace data scientists, but is try to scale the data scientists. It is an assistant. Firstly, it starts from the data scientist domain knowledge. It tries to materialize your expertise. So this will then, like for example, if for yourself, you can only solve one problem at a time. But if you materialize your knowledge and kind of open source it, then you can simultaneously maybe solve 100 problems. Then you scale your impact. The second reason is that AutoML try to automate the workflow. Imagine that your daily work, you will train a model and see what the feedback, the validation, and try to change the feature a little bit and train again and see the validation and change the feature engineering a little bit and do again. This is like the very routine work. But how about if we can automate your workflow? Then it will improve your productivity. Like you maybe can simultaneously run tens or hundreds of jobs to solve more tasks. So in this two perspectives, we think that AutoML is trying to scale machine learning expert scope. And with more machine learning application landed in the real world, the industry's efficiency will be improved. So it's also a win for the industry. We make the cake bigger. So in that way, we think that this is a win-win for both machine learning expert and the industries. Okay, I just explained a little bit about why we propose the AutoML. So what is AutoML? This is just from the name, it's automated machine learning and try to accept, but it has two goals. One is to accelerate machine learning research, and the second is try to make machine learning available for everyone. I'll try to explain these two angles. This is a very standard machine learning workflow. We start from feature engineering, and we then design our architectures. And after that, we do some hyperparameter tuning, meaning training the model and to optimize the weight to get the best validation. And then we do model selection and maybe ensemble it to make a better generalization. And last, we try to compress it or export it to meet the serving requirements. So I would say the first two stages is very important, or we take most of the time on, especially the first stage. The first stage, I call it the hardwired architecture optimizations. Because in this stage, what we do is try to make the hard connection, try to design the hard connection of the model. Even you do feature engineering, it's kind of do this way. Hardwire means like you decided, hey, this feature just do it this way. For example, for this feature, you just do log transform. For that feature, you just do embedding lookup, something like that. It's decided. After you decided, even when you train your model again and again, you only train the weights. You won't change this hardwire connection anymore. But for us, we think that this part actually has the most potential to improve the quality if we can make the design more efficiently. But we also want to tackle the second one, which is most people are doing like training the weights or parameter and try to optimize in some way, like tuning the learning rates, the dropouts, all those things. But today we may most focus on the first stage. And this stage is also what our research firstly try to tackle. And for this stage, the challenge is like this. Firstly, those connection design is commonly not differentiable. For example, you cannot say, hey, from your loss, you try to optimize the connection. Say, hey, maybe next time I don't do log transform. I do normal distribution. Commonly, we don't do that because it's not differentiable from your loss, commonly. And another problem is that commonly it's multiple objective optimizations. You may have a label, but when you really use that model, especially when you design the architecture, it's not just the label itself as a target. For example, if you design a model for on-device or mobile usage, there's definitely another constraint is the latency or battery consumptions. This one should be considered here because if you design a huge model, then your latency cannot meet, even you optimize really well. So we want to get all the task-specific objectives down to this architecture search, architecture design stage, and try to optimize them all. So this is the challenges. And for this solution, it's a little bit like the evolution, I would say. I will explain this graph a little bit. How we could do the architecture optimization by this loop, and how it's like the evolution. Firstly, we call this architecture as the DNA because it's really like the DNA of us. It's just a sequence of information. Based on this information, in your we want to have the first component, which is named the DNA to model synthesis. This is really like the protein synthesis. It's like given a sequence of information. How could you just based on this information generate a graph? Graph meaning the TensorFlow graph or model graph, like generate a model design. Like say, hey, this feature do this, that feature do that, and the dense layer fully collect and logit. Those kind of model design. How we want this component do this thing, like based on a sequence of information, generate the whole graph design, the hard connection design. If we can do this for this component, then at the training time, we can input DNA, this sequence, and automatically generate a model. And then the second component is try to validate the model. Validate could mean like you train it and use a validation to validate. It could mean other things. For example, for the on-device context, the validation may means you run your model on an iPhone and get the latency from the iPhone. This could be another validation to validate its latency. And you can validate its memory, its model size, a lot of things. After you validate all these things, you may get some feedbacks. Maybe it's just the accuracy, validation accuracy. Maybe it has other components like the latency. And then we combine those feedback together to generate a single feedback. Say, hey, this DNA is good or bad, or it's good for the environment or not, like our human, right? Our human validation is like you live in this world. If you successfully live at 80 years old, then you are good. If you are not, maybe there are some problems. Yeah, we do the similar things. We give the feedback, say, hey, this DNA is good or bad. And how good it is a quantized validation. And then at the controller side, this side commonly is our human brain. Like before the AutoML algorithm, our human brain plays this role. But now there's an algorithm named the DNA optimization. He consumes a lot of those like DNA feedback pairs and try to figure out which DNA design is better than the others. And then after he's updated or optimized, he will generate more DNA which could get better feedback. This is the DNA optimization's job. So you can imagine that if we can turn on this loop, with the time goes on, this controller or the DNA optimization algorithm will generate better and better DNA. So we kind of make the design better, or design a better model than before. This is how AutoML algorithm works. I can give you some examples of like how could it impact the real problems. The first one is ImageNet benchmark. The green box is like human design. Like human is the controller. Like real brain is the controller. And they do a lot of experiments and try to figure out, hey, this is better than the others, and they change the architecture and do it again. And this is better. The X is the timeline. You can see how fast they can get. The Y is the top one accuracy on ImageNet. And then when AutoML kicks in, because it's more productivity, because you can let it run. They can run 24 hours a day. And they just run, and you can use a lot of computation to run it. Ultimately, they will get a better design because of this loop. or evolution. So it can show better accuracy. At this example, the feedback is accuracy itself, like saying only accuracy as a feedback. I can give you another example. When feedback is not just accuracy. This is like the state-of-art on-device vision model, which also developed from our team. Compared to the previous state-of-art, which is MobileNet V2, also from Google, this model is like at the same accuracy. It is like almost 2x faster. This is a really good achievement. And how could we design this? Is like when you have a model, you validate from two directions. One is the validation accuracy. The second one is we send this to a specific Pixel phone, Google Pixel phone, and let the Pixel phone run the model, like run one inference, and get the latency back to as a part of the reward. We want to reward faster and accurate models. We combine these two signals together as a reward to the controller. So the controller is trying to figure out how not just the most accurate model, but also very efficient model. That's why we get this. Another example is like we also work with the Wemo and use the same infra, try to improve their car's vision models, because they have a lot of vision models in their car to detect a lot of things. And they already have very, very strong baseline because there's a lot of cars driving on the road. Their accuracy is really good, but we want to, on top of that, continue to improve the strong baseline. So we apply this loop, and we successfully improve their LiDAR segmentation and traffic line detection model. And we are trying to improve more, because if you can improve one, the algorithm is very general. You can apply it to a lot of tasks and without any domain knowledge. And it reduces their error by another 10%, which is really good. And it deploy on their fleet. But this ideal algorithm has its limit. We call it AutoML research because it starts from the research. And for research, we only, for example, only try to solve one problem at a time, like ImageNet. So researchers commonly customize the DNA to model synthesis and the feedback designs. So for example, if you jump to another task, maybe researcher will redesign it, and we haven't come out with a very general design which can cross-task to work well. And it's very tricky. How to design this DNA to model synthesis, like give a sequence. Why you should do this, like construct the model as a burger instead of construct it as a tree? There's a different topology. Why you do this way? This is very tricky, and based on very strong expertise. So this is the limit. Also, the DNA optimization is very low efficiency. Maybe some of you have heard that the first paper of the AutoML NAS paper, it takes 450 GPU run more than a week to solve CFAR10 task, which is a very small task. So it's not efficient enough. This is another direction we try to improve. So because it's low efficient, we can only apply this like search and the loop and the evolution on small tasks. We cannot afford to do on very big tasks or even the real-world industry task. It's because you train a single model will take maybe months or a couple of weeks. Then we need thousands or tens of thousands of iterations. That means a lot. So, but we are trying to improve that. Okay, so AutoML research only solve half the problem. Ultimately, we want to scale machine learning with AutoML on these two dimensions. One is push the boundary of research, meaning better model, better quality, better accuracy. Another dimension, we also want to scale machine learning in more real-world problems. So how could we make machine learning available for everyone, like meaning the X directions? That's the motivation why we propose another definition of AutoML, meaning AutoML as an AI product. This product is like this. with a couple of clicks, everyone could build a high-quality AI model to solve customized problems with AutoML. I highlight the everyone, high quality, and it can solve customized problems. Meaning it's not like a general model, but it can customize for your specific problems. So we think the product like this way, it's on top of our research result and build a very user-friendly and affordable product. This is another constraint on top of the research. We want it affordable, meaning it's not 450 GPU a week, that kind of cost, right? It should be tens of bucks or $100, that kind of cost. And it can massive scale machine learning applications in real world. We think that if a product can meet this 4 criteria, it's a good AutoML product. Firstly, it's an end-to-end automatic modeling, meaning data in, model out pipeline. You consume the raw data and directly generate a model could be serving. And 0 human intervene of the pipeline. And you have competitive quality. It's not just help you automate the workflow, but also on top of that, we want to help you achieve the top qualities. Like, for example, it could rank at least the top 20% among human experts. We don't want to achieve the first one, because they definitely need a lot of human expertise if you want to really achieve the top 3. But at least we can achieve the top level. And but the benefits of it is that it covers 80% of the problem in domains. If you are talking about image classification, AutoML, then no matter the data set just have thousands of images or millions of images, whether it's a medical, cancer scan, or some like a Disney cartoon image data set, it's all covered. Like, there's no excuse. You should cover major of the problem in domain. And last one is the budget flexibility. Like, because there's a long tail customer and a head customer. Some like long tail customer may only want to pay tens of bucks. So you need to have a solution for that. And or of course, we need, if the customer want to pay more money, for example, the 100K, you should give a quality with 100K. You can scale with the budget. So the user experience is mainly like this. For example, for the vision, for the image classification task, it's like you just need to firstly prepare your data set and your labels, like, or label the images and update it to the product. And then you set up the budget, say, hey, I only want to train $100, and you just click the train button and it's done. And the whole system just automatically run. And during the run, it will give you some monitor validation metrics, like what's the current accuracy and what is the validation other metrics you care about. Even the metrics are automatically selected by you based on your description of the task. For example, you say classification, and if it's a single label, we give you accuracy. And if it's a multi-label, we give you PRAUC, something like that. And after the model trained, there's a very simple interface that you can directly serve the model for the prediction or for the batch inference. So just 4 steps without any code. And if you look at the back end of this product, the key part is like this function. I call it AutoML function, and it accepts 2 inputs. One is the data set itself, and the second is your computation budget. Say I only have a single machine, or I have 2 GPUs, something like that. And then the whole pipeline just automatically run it and return the model already ready for the prediction or serving. If we zoom in this function, what we actually do behind the scenes is like this. We just automate every part of the workflow our machine learning experts are working on every day. We automate every part, and we try to make sure that the quality are very good. So we may do automated transfer learning, automated feature engineering, architecture search, hyperparameter tuning, ensembling, and compression. Yeah. I can give you one example. which is the first product I launched, named Cloud AutoML Vision, how we automate each part of it and how we make it. For the first part, definitely for the vision task, we want to directly use transfer learning instead of feature engineering and architecture search. Because for vision task, it's very, by nature, very natural to do transfer learning from task to task. And by using transfer learning, we can save a lot of efforts. For example, it converges fast, so we can make it more affordable. And because we have prior knowledge, our quality works really well, or generalization is really well. Even user provided just hundreds or thousands of images because we have pre-knowledge. So that's why we decided to choose transfer learning. And we push this even further for the pre-trained weights. We used to use ImageNet weights, which is already very good. But we then turn to use the Google level data pre-trained weights. In Google, we have a huge data set, which is, you can imagine all the images in the world, in the website, in the internet. And we have some very weak auto labeling, kind of like Facebook is tagging. In Google, it's like tagged by the knowledge engine. Like it's based on the web page's text. Because on the text, there's a knowledge engine try to extract what this text are talking about. Like this is Yosemite, this is a hiking, or something like that. And because the image is surrounded by the text, so we use those knowledge entity to tag this image. Say, hey, this is Yosemite image, because it's surrounded by the text mentioned about the Yosemite. So, but it has a very, it's very noisy, like the Facebook is tagging. But we use this as a pre-training. It has 100 million to billions of images. So we can train for a really long time and get a like perspective of how the world's image looks like. And then we're fine-tuning the weights on customers' task based on this initial weights, which works really well. And we use the state-of-art architecture found by the AutoML research, which is a NASNet, which is 82.7 top 1 accuracy on ImageNet at that time. And we scale the pre-processing pipeline to support any number of channels, because commonly when experts do vision tasks, they were limited to like 3 channels, meaning RGB images. But as we want to tackle all the image classification in the world, we have to assume that there might be some tasks only have 1 channel, like the grayscale images. Or there are some weird tasks have 15 channels. That happens in Wemo, because their data set is not actually a real image. It's a fake image. It's their LiDAR signals. They have a lot of LiDAR, and they use the spatial dimension to match 15 LiDAR signals into 1 image. So it's a 15 channel, which really weird. The human cannot read it, but we still can train on it. Yeah, and we fine-tune all the weights. And for the weights, we only do a very narrow range grid search for the learning rate, and we use a cosine learning rate decay, which save us hyperparameter tuning space. Because if you use exponential decay, you may have 2 hyperparameters to tune, but for cosine, you only have 1, which is the total steps you want to train. And they'll draw a cosine curve to decay the whole learning rate. Yeah. And for the model selection, we also automatically decide the training step. So the human even don't need to give the training step or epoch they want to train. We automatically estimate based on the data set itself. For example, how many images it has to automatically give a ballpark number, and we continue eval the training stages, and if it's already converged or start to overfitting, we stop it. So give you the best model. So in that way, you don't need to know anything about machine learning. Just click the train button. Yeah. And yeah, this is and what's next? After we deliver the vision task, we tackle another interesting machine learning domain, which is structured data, which, for example, like the house pricing prediction is a very standard one of this. Like you have a table data. Each column is a feature, is numerical, categorical, and you have another column which is your label, and you want to predict. It could be a ID, which is a classification problem, or it's a numerical, then it's a regression problem. And actually half of the Kaggle computation can fall in this domain, and it has very good, huge business impact. That's why we want to also work on this. And from research perspective, we are trying to build a kind of Kaggle bot. Hopefully, we can achieve this, meaning it could be a bot join any Kaggle computation. It consumes directly from the CSV file the Kaggle provides, and after running it, it will generate a CSV for submission. Then you submit, and you get a good rank. Then I think it's very good way to prove that this works. So that's why I mentioned this is not just for automate everything, but also on top of that have a good quality, which is our goal. Our goal is try to achieve at least the master or grandmaster level of Kaggle across multiple tasks with the same pipeline. We're not yet we're not there yet, but we are working on that. Yeah, I would say because this product haven't been launched, it's launched next month in Cloud Next 2019. So I cannot say too much about this. Yeah, but our research goal is try to get the top level across multiple tasks with the same pipeline. And then another interesting direction is IoT, which is like, can we automatically design a better model for the on-device context? Because on this context, you have more constraints besides the accuracy itself. You need to consider battery, the latency, a lot of hardware things, and there's a lot of different hardwares. There's ARM, there's XA, and there's a different like TPU, different things. So you have it's a limit our because you have to have an expert know both. You know the hardware well and then know machine learning well, then you can manually design a good one. But with this method, maybe we can scale to design different architecture for different hardware platforms. And the third one, not the least, is we still want to make the optimization more efficient. Then maybe someday we can give up the transfer learning, but directly search on your task, which will definitely give you better results because it will design the hardwire architecture specifically for your task, which could work better. And the takeaway is that AutoML is try to scale ML. And we want to scale in two directions. One is the boundary research, and the second is the real-world problems. We want to solve more. Thank you.
We have time for a few questions, so please raise your hand and we'll give you a microphone.
Sorry if I missed it. Is AutoML fundamentally different from using genetic algorithms to search in a topology space and hyperparameter tuning? So that's not one question. And two,
sorry, can you say the first question?
Is AutoML fundamentally different from genetic algorithms and using that for topology, finding better topologies and hyperparameters?
Yeah, it's leveraged a lot of ideas from that, but it's beyond that. We try to build a toolkit or a suite of those controllers. It could involve the traditional evolution algorithm, which may be similar to what you mentioned in the generic, like you mutate it and you hear it from the father to the son, do like human evolution. Yeah, we also try that algorithm too. But there are other ways to do this goal, to achieve this. It's like reinforcement learning can also do this. You based on feedback, you do policy gradient to optimize this non-differentiable weights. And we can do it, there's even other ways. For example, random search could also be one way. It's just ignore all the feedback. Yeah, and or Gaussian distribution. There's a bunch of ways. We just want to build a toolkit and even try to figure out some better way, because for evolution and reinforced learning, both of them suffer from the low efficiency problems, which is very bad for us right now to improve the usage. Yeah, we try to make a better way to do this.
What's like the building blocks for your DNA, like the GATC, I guess? Like, is it just like a layer of like convolutions, or like what kind of fundamental architectures can you put into your architecture?
The building blocks do TensorFlow, of course, but we because commonly we directly write TensorFlow code, like we build conv, or something like batch norm, something like that. We write it. But in this context, we try to not directly write it by human, but controlled by data. We firstly, or by a proto, we define a data structure, and we try to use this data structure to generate the graph, meaning use data to control the binary flow, the code flow. Because in this way, we can iterate the DNA, mutate the DNA, then use DNA to generate the new model automatically instead of human write it. But I can give you an even simpler example. For example, you can define a Boolean. Say, if the Boolean is at the first place of this array, for example, the data structure is an array, then if the Boolean is true, then I give the first layer conf. If it's false, I give it identity, meaning just pass it. This is the simplest way to how to do the DNA to model synthesis. Yeah, this is a tricky part I mentioned before. Like this part needs a lot of heuristic and domain expertise. Like you cannot arbitrarily search the whole thing. You have to have some limitation. Say, okay, maybe the maximum layer is 6. And you say, hey, for each layer, it's just like a burger style. One layer after another, no branch. This is all, for example, your definition is part of the DNA to model synthesis. Yeah, you say, I don't do this way, I only do this way. It's already make your human heuristic choice. Actually, this is very helpful because this helps reduce the search space. And the core reason is because the controller algorithm is not efficient enough, evolution or reinforced learning. So you cannot afford to search everything. Maybe later, if we can improve the controller algorithm, we can affordable to search more arbitrarily. Like say, even the circle shape is okay if you do that, search that, yeah.
Hi, thanks for the great presentation. So neural networks are black box, and AutoML seems like a black box to generate new black boxes. Are there any efforts to understand how to debug these models if they don't do well, or why are they giving a result for a particular example?
Yeah, I think you provide a very good point. Like, if we want to convince the industry to use, we have to give them the explainability. Yeah, we definitely consider that. We could do that, for example, but we haven't had it. But I guess through the product journey, more feedback maybe from customer, and maybe we'll add it. I can give you some ideas like what we are thinking about to give explainability. For vision task, you definitely could use attention to build this, like why the model try to give the true or false, because you can train attention on your images, and you can base on this attention to say, oh, because they focus on this part, or this part is hot, and then they make the decision. This could be helpful for the medical image classification. If the model says you have a cancer, then I want to know which part give you the support you say it has cancer. So attention could help this. And for structured data, the common way is like you can have some feature relevance, like this feature is relevant. It could have two levels. One is like the data set level. Like through the whole data set, what's the feature importance to give you say, and I guess you are more interested in the per example case. Like for this specific example, you predicted 2. Why is this? This could, one simple way is that you can mask out each feature to do inference. And if you see that your number drops, your confidence drops, then maybe that feature contributes the most for these specific examples. And another very interesting idea we haven't fully explored is that could we distill a neural network, which is a black box, into a decision tree, which is a white box. I'm not sure that this distillation is like you derive all the knowledge of the mother model, like all the quality of the mother model, but you change your shape. If we can change that shape into a decision tree, but it has a similar quality as a neural network, then it becomes explainable, right? Because in high chance, they will predict positive at the same example. Then we explain, hey, because this. But we haven't fully decided. This is a very interesting idea, yeah.
Okay, let's thank our speaker again. Okay, let's just move right along. Let me introduce our next speaker. His name is Matthew Toven, and he's a principal member of the technical staff at Salesforce as part of the Salesforce Einstein platform. And he's a co-organizer of the Scala Bay meetup. And he's going to be talking to us about the Transmogrify, which is another AutoML open source project.
Thanks a lot for introduction. Can we remove this sidebar with participants? That'd be cool. So thanks everyone for coming. I'm so delighted to see so many people here. I was thinking, it's a meetup, probably 10 people will arrive. I totally underestimated how many people there is in the city and interested in ML and AutoML. So yeah, hi again, I'm Matthew. I work at Salesforce, and today you will learn what Transmogrify is and how and why we build it, and you will go home and try it out. So it's open source, you have no other excuse. So before we begin, I have to put this slide here. So it's a forward-looking statement, don't read it. Well, can I read it? I will summarize it for you. So if you go home and want to buy some stock or build a product, make sure you kind of consider other things rather, not only just this presentation. And it might have some futuristic view on things. So what is Salesforce? I don't know, probably everyone knows it, but I can kind of give an idea what problems we have at Salesforce. So Salesforce is a multi-cloud, multi-tenant environment. We have a ton of data. We basically sit on data, and every day we get more of it. And then this data is super different. It's extremely diverse. We have customers from Comcast, Fanatics bank industry, government industry, and of course a ton of nonprofits such as American Cross. All of them has different ideas, different work. Oh, thank you. Yeah, different user bases, different work processes, and a ton of different problems that they tackle. Same goes with machine learning. So definitely one size doesn't fit all. And then this is what we actually started doing. We actually went on the journey of building an Einstein platform, and then we learned several things that I present kind of summary, very short summary. One of them is like customer-specific models, bit global models. Second thing is majority of business data is structured, and then too many use cases and too few data science. Already mentioned in the previous presentation. And we learned this the hard way also, because we started doing it manually, and obviously it didn't scale. So the first thing is that customers really care about privacy. And it's a very hot topic now, also ethics in AI, and we kind of talk about it a lot. And then for Salesforce, we just see it first line. Every single customer come over, they would go and ask us, what about privacy? how can we look into the model, how can we make sure the scores are good, and then how can we make sure that the competitors don't use the information that we have. So we assure them that it's not shared, and it's indeed the case. And then every customer data is actually different. So same data that we have for American Red Cross won't work for other nonprofit organizations, such as College Forward. Same for the banks and so forth. Second is that majority of business data is structured. So this is a Kaggle survey from 2017. And there are newer results now, but it's pretty much the same, repeats the same ideas. We have a ton of data. Most of the data is in relational databases. So it's already in a really great format. So we can use it and build good models on top of it. And then third thing is actually as we go and build those models, again, was already said, that the process of building models is very tedious. And they're all the same. You kind of start by data prep, feature engineering, feature selection, model training, and then you do some evaluation and ship out eventually a model. The model has to be refreshed once in a while, quite frequently for some tenants, quite infrequently for others. But then you repeat it all over again for every single tenant, every single customer, multiple times for every single sub-org that they have. So it's actually a ton of models that you have to build to actually provide good predictions. So at this point, I hope I kind of convinced you that one person or one team or even 10 teams won't actually tackle that for 300,000 Salesforce customers. So this is how Transmogrify was born. We wanted to build specific models and structured data and then scale the data science as a platform offering. So Transmogrify kind of tackles several things, and these are the main three things that I want to talk on this presentation. Is about automating feature engineering, feature selection, model selection, show you the abstraction on how we thought about feature engineering and expressing machine learning flows with Spark and Scala, how we built in model explainability. I didn't actually cover this well, but I will try to show it in a demo. And then the main thing is actually giving a really good accuracy comparable to human models, but most importantly, reducing the time you spend for building those models. We don't want people to spend weeks and weeks of trying to fine-tune models. We want this to be automated. So on the right, you have like a super tiny snippet of how Transmogrify code looks like. This is actual code, and I will show it at the end. How simple can it be, and then how can a data scientist or a user can explore this code to make more sophisticated, customized flows if desired, because it's just a universal tool for build machine learning. So what's in the name? It comes from a comics from Calvin Hobbes. I actually didn't read it when I was a kid, so one of my coworkers, Leah, was a big fan, so she proposed, and we got this name in. So it's something that you would go and transform in some magical way. It kind of fit the idea of what Transmogrify is, because there's a lot of magic in machine learning. So what Transmogrify is and how does it fit in the platform that I'm a member of that team? The platform is actually a large, big piece of software, poorly connected, closely connected, somewhat connected. Transmogrify is in the heart of the platform. It runs the AutoML for a ton of applications, and I put some examples on the top, such as lead scoring, case classification for Service Cloud, engagement scoring, and prediction builder. And prediction builder is actually quite unique because it's somewhat a very general way of defining AutoML. So it might resemble what a previous speaker just mentioned about how can we actually make it a product. So we actually were crazy enough to go and build a product like this, where you specify one table, let's say, I don't know, opportunity, and then you specify a column that you want to get a prediction on, and you go next, 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 and that's it. You got a model. There's no involvement of data scientists or anything like that. So kind of impossible, and it's actually somewhat possible. So under the hood of Transmogrify, I'm going to talk about three major themes. There are more. I kind of selected some of them. So I'll talk about automated feature engineering, feature selection, model selection, and then we'll see a demo at the end. So for automated feature engineering, before we tackled that problem, we actually went ahead and defined the machine learning type hierarchy for all the type that we thought are important to do machine learning for structured data. if you go and look on any type hierarchy in any programming language, it will actually look very different, and it will actually look very common for all the software engineers, but it's not suitable for machine learning. Here's an example. Let's look on a binary feature. It inherits from numeric. Does anyone know any programming language where you have binary that inherits from numeric? Probably not. But for machine learning perspective, binary is a numeric for all the purposes. It's 0 and 1. So it should behave as it's a regular numeric value. And then you can use cool functional properties on it as a monoid sum and then implement counts very easily. And then, for example, pick list is a categorical feature, which is a single response. So kind of resembles the single value from a closed set, like an enum. If you are curious what the names are, why it's like a multi-pick list, and what are these weird names? So these are not weird. These are actually generic Salesforce types. And we kind of said, those types are great. Salesforce proved itself to be very successful for a ton of applications. So we're just going to take the names and put them into a hierarchy. And it worked well. So after we have the types, we can now use the types to actually do pretty sophisticated feature engineering using the polymorphic qualities of the types. So for example, if I have a phone number, I can immediately, automagically, or using the transmographer, actually create a extractive country code or check if a phone number is valid. Or if it's a numeric feature such as age, I can automatically bucketize it based on the distribution of values in the data set, and so forth. So having this framework actually allowed us to start expanding machine learning and grow it as a library and integrate it for different projects. So here's like another example of numeric computation, for example. Very standard technique, which every single data scientist kind of knows, and maybe will go and implement it him or herself. But why would you do that if you have already an implementation in the library? And this was pretty much our thought about this. So for example, for categorical values, we would do one-hot encoding on the values and put them into different columns. Kind of put some more examples of TF-IDF, pretty standard. And for example, for date features, usually when they're encoded as numerical values, they don't give much prediction power for most of the algorithms. So we found a very cool method that, well, kind of it's a paper and that worked really well for the majority of the algorithms, and we implemented the library, and works for all of our customers by default, where we encode dates in the circular transforms, and then for each of those values, we would get a coordinate, which actually becomes a categorical feature in a sense. So what the transmography provides actually provides a good library, good foundation to start grow your standard tool set of machine learning techniques. And these are some of the things that we already have, as I already mentioned. And then, for example, right now I'm working on the reverse geocoding to provide some kind of knowledge around geo points that we receive during our data population. So next step is automatic feature selection. So once we have all the raw data from database extracted out, we created some of those magical features. We actually want to go and evaluate those features, how closely they related to a label or not. But guess what? There's a ton of problems. So I kind of went and mentioned some of them, especially for enterprise. And why is it different for enterprise? You will see. I think would be quite self-explaining. So first of all is a hindsight bias. So this is like the oldest probably Salesforce UI. It's called well, not UI. The schema is lead. It's what salespeople use to actually manage the groups of people or product to offer their service. So when salesperson calls it whatever defines the lead, they would before the lead converts to opportunity, basically, okay, a person is likely to buy an insurance, for example. A salesperson would go in and fill in the deal value. So what happens is that this field becomes a leaker. It closely correlates with a label, and it kind of becomes a stronger predictor, and then model overfits on that value. But in the real life, it has no no actual value. Once you start using the model performance drops significantly. So it's very important to actually identify those leakers during the model training and exclude them. So yeah, in layman terms, like, you know, traveling to the future, taking the book, going back, training that, and yeah. Second problem is the customers use field incorrectly. So they say, oh, sorry, that's actually a different one. Field usage changes over time. So maybe a process that customer had one definition of the field. The new Salesforce administrator comes in, they change stuff. The field usage changes, or maybe a new group of developers comes in. So the data population process starts delivering different values for us, and then model quality obviously drops. So identifying those features is also important. Problem third is the bulk upload. So sometimes customers join Salesforce, they start slow at the data, and maybe at some point they actually upload a large number of data. And then what happens is that your distribution of values changes drastically. Again, model quality will suffer, and then identifying those things is very important. And what also happens is that the bulk uploads usually have like sequential timestamps, so that's super ugly to handle. And then problem 4 is actually, yes, the feature types misuse. So feature defined as text, you think it's a text, you kind of start treating it as a text, you kind of tokenize it, but and you know, one hot encoded, but it's actually not a textual feature. It's actually a categorical. So identifying the cardinality of the values in that field, very important for actually automating machine learning for such type of data. Okay, so what Transmogrify does? So Transmogrify, during model training, we actually compute a bunch of important statistics that we keep together with the model, and then the same statistics can be explored by a data scientist or a user through the record insights or actually model insights. So we actually go in forward with actually also improving it and increasing the number of statistics and things we compute. Now, next thing is, you know, we actually look on the distribution of each feature value, and then feature correlation and weights, and we're trying to remove the ones that have low predictive power or versa. So kind of, I don't like this slide. I just put some of the images of different techniques that we do for different features. So for example, for categorical features, we'd go compute Cramer's V and Pierce correlation. For numerical, we'll try to do auto-bucketization, Shannon divergence for regular numerical features. And then based on, why did I put type hierarchy here? Oh yeah, and based on the type hierarchy, we actually compute a different lineage of feature engineering, and then we keep this lineage also together with the model. So it's also explorable by users once the model is trained. So it's kind of very transparent in this sense. It's not really a black box. Some of things actually black box, especially when you hash them. And that's very important to actually keep the original values together with the model, so I can actually see what went to that hash value, what is the hash group. So what does the label leakage look like, for example? So you train 2 model types, for example. They look great during your training time. They perform excellent on a holdout data set. So holdout is the data set that you kind of pick and put aside. You don't use it for training. You just use it for evaluation during the training time. And then once you actually go and evaluate your model against the actual data, that's where the model drops. And that's where the customers start to suffer and say, oh, your model sucks. So with AutoML, it looks like this. So overall quality of the model originally might not look great compared to the hand-tuned model, but when you actually evaluate it against the real data, it works better. And why is that? Because you remove the leakers, you remove the features that have no importance, and so forth. And this is like a kind of showdown of an actual customer model of AutoML versus the hand-tuned. So we had a couple of data scientists that sat and they inspected the data frames and looked on the data of several training sets, and they actually identified together with the customer. So the white one, some of the white ones actually customer identified. They were not captured by the AutoML, and then AutoML found much more features that were not identified by the data scientist. So we want actually them to fully overlap and then hopefully we'll all get smarter, and AutoML will get as smart as us, or well, something good will happen. So yeah, this is like another example of evaluation of a model where we took AutoML without label leakage detection, and this was the red line, and then we actually did the sanity check-in that actually eliminates the label leakage, and it overall performs much better than the hand unit or the model. So for the model selection, obviously we kind of follow the standard stuff, like different grid searches that we do for different algorithms. Currently we support all the Spark standard algorithms, plus XGBoost we added recently. And then you would be surprised how important it is to actually benchmark all those algorithms. And then some customers, their data is suited better for certain types of algorithms. And this is just a diagram that actually shows that different hyperparameters and thresholds that you actually set into the models influence drastically each of the customer model performance. So I had to remove the names on the x-axis. Now let's see a demo. I will probably have to stop presenting and then present some other screen, I think. I don't know how to do it here. First time I'm using this WebEx. Okay, here, share my screen. Share my screen. Oh, that's good. Oh, here we go. So here's a Titanic data set from Kaggle. It's a binary classification problem. We have a list of passengers of Titanic, and we want to predict who out of the passengers survived or not, and what were the contributing factors to that sad or maybe not so sad event. So with Transmogrify, as I promised, the workflow itself is very short. So it's not only for the demo, it's actually all the programs like this, they're pretty much short. So you start by defining type, in this case the passenger. So whoever is familiar with should I increase the font? Yeah. Okay, let's try do this presentation mode. Okay, cool. So passenger is like a project class, just container for all your information. Has some artificial ID, it has a label, if person survived or not. Passenger class, name, sex, age, siblings, spouses, partner, children, and so forth. So with Transmogrify, it looks pretty much like this. You spin up a Spark session. So in this case, I have like one argument to application that I provided to the reader, passed to the data. The data is CSV. So I have a very handy, simple reader for it. I'm doing like, okay, CSV reader of type passenger. Then what I'm doing is that I'm actually materializing features. So we have we introduced an extra abstraction from what Spark didn't have as a feature abstraction. And feature is basically a pointer to a column in a data frame. It's a type-safe pointer that provides you a way to modify and create features manually or automatically on that data. So in here I'm doing like, okay, just go Transmogrify, go automatically create me features, and it would return me an array of features. I don't know why is it not. Okay, let's do. After that, I'm actually applying the sanity checker. So sanity checker is the component actually responsible for cleaning up the data and detecting the label leakage. Here I'm creating the model selector, stitching it all into the workflow and printing out. So here I'm doing workflow. I think I'm doing workflow. Yes, workflow.train will produce me a model. And then on the model, I'm printing out the shortest summary I was able to combine from this. It has actually much more methods you can do, like model.summary, model.insights, and then start exploring different things that are computed by Transmogrify. So if you run this, okay, yeah, you can see that. So if you run this, the command is pretty simple. We have a script to run this. So I'm doing like a local Spark submit with this, and I'm providing it with the CSV file. It will print out a lot of stuff. This is Spark, not us. And here at the end, we're printing out the short model summary. So we're showing what did we do here. So Transmogrify in this case evaluated two model types, logistic regression random forest, using the AUPR metric, total 18 random forest and 8 logistic regression models, shows you the average range of those model performances. And then it shows the selected model, what in this case was logistic regression, the parameters of that model that was selected, shows the performance on the training set and the holdout set, and then it shows actually top insights. So for example, if a person happened to be a female, was more likely to survive. And then negative, if you were a male on the Titanic ship, you actually did not survive, most likely. And these things we actually kind of know from the Kaggle results already. You can also look on the top contributors and so forth. So Kramer's V stats, again, shows the same things. So what you can do with this is kind of limited mostly by your imagination. Because what we did, we actually didn't go far from Spark. And then anything you can do with Spark, you can do with Transmogrify. You can mix and match workflows and stuff. You don't have to use all the abstractions. And then here's another example, Titanic, same Titanic. You can be more robust and more explicit. You can go and define every single particular feature without using the automation and do feature engineering. Yeah, so this is how feature engineering looks like with typed features. So once you have pointers to features, in this case I have sibilance poses, which is a numerical feature. Yep, so it's called a feature of type integral. I can actually suddenly use plus operators on them. And then you operate on them as if they are regular variables in your program. Same with categorical feature, for example, I can call a pivot method on it, and maybe if I have, I can actually do my custom feature engineering, which is just h.map, and I want to make it a pick list. And the way I do it a pick list, I just put a condition and map it into two categories, and so forth. So it's very, very easy to mix and match, and it's typed. So the compiler will actually tell you what's wrong with your program, which comes very handy if you actually run in your applications for hours. Okay, so let me wrap this up. So how well does it work? It works pretty well. So we currently shipped 4 applications on Transmogrify, and most of the models deployed in production completely hands-free, so they fully automatically generated from the data-driven models that create applications that actually train models. So kind of long chain of events, but we currently serve around 5 billion predictions, and actually changed since Mark tweeted about this. So what do we do next? So we're going to go and implement more insights on scores and models using Loco and Lime, and maybe some other techniques. We will improve our parameter search. We're actually working extensively on model portability. We're trying to make models more portable, so once trained, you can serve it elsewhere, and not only in Spark. It's currently possible to serve it from any Java process, but we actually want it to be maybe in a separate runtime even. Of course, perf tuning, bug fix, and so forth. So where do you go, guys, next? And gals, of course. Read the blog post. This is the announcement of the library that we did if you want to know more. But I think the most important, just try it out. It's up there, transmograph.ai. You can obviously contribute. We're very open to contributions if you like Scala and Spark. If you happen to be a student and currently looking for what to do in summer, we have a Google Summer of Code application, was approved recently, so we're going to be there with Transmogrify and 2 other projects, and we're actually looking for somebody to contribute, and Google will pay money for this. If you're feeling creative, we actually need a logo. It's kind of embarrassing we don't have a logo. And then, yeah, if you have questions, let's do it now. I think I have a little bit of time. Yeah.
Hey, Matthew, since I have the mic, and I got 2 questions first.
Yes.
So the first question is that
it's not a setup.
The models only for the traditional machine learning model, not the deep learning model. Is that right?
That's correct. The thing is that you can do TensorFlow and deep learning because it's just Spark. So you can use TensorFlow Spark estimator and then train your deep learning as if it's a regular transmogrify stage. So that's why I'm saying there are no limitations really.
So the second one is after the feature engineering you generated from the framework, do you store them anywhere, or is it going to be training every single time, so always from the start?
Yeah, it's a good question. So right now, if you just use it out of the box, it's completely stateless. The process starts up either locally or on the cluster, loads the data, computes all the statistics, computes all the everything that's required, and saves out the model if you'd like. You can also save intermediate things and then maybe actually load them while you do it next time. You can always use that, checkpoint in with Spark. So yeah, you can do that.
Okay, thanks.
Questions, go questions. Questions 1, question 2.
Yeah, I was wondering, why did you pick Scala as a language?
I've been asked this question the most, I guess. So I'm a software engineer, and I like my code to be awesome. And to make my code awesome, my best friend is a compiler. So he actually checks my code for me. So I know Python is kind of more user-friendly for data scientists because it's very easy for prototyping. For platform-level projects such as Transmogrify, which is used as a platform offering, we actually had to use typed language. So
I love Scala.
Yeah, that's it. Okay, thank you very much. I have a last slide. Thank you.
Thank you.
Okay, our third talk. Our speaker is Fei-fei from, he's a staff software engineer at the IBM Center for Open Source Data and AI. This is kind of a sequel to a lightning talk we hosted about a year ago talking about deep learning and medical imaging. So he's going to catch us up on the project since then.
Hello everyone, my name is Fei-fei. I'm from the IBM Center for Open Source Data and AI Technology. Today I will give a talk about our deep learning approach for mitosis detection from big medical image. Okay. Before I start, I will give a little bit of information about our center. So our center was launched on 2015, and we have about 36 software engineers working on the open source project, such as big data, deep learning, and machine learning platform. We have 3 Spark committers for the Spark, SQL, and PySpark. And we have a few people working on the model asset exchange project. That project develop and create deep learning models and wrap them as a REST API for end user to use. And we also have some FIDO project to train the deep learning model on the cloud. And another project named Jupyter Gateway to connect the local Jupyter to the remote cluster. You can run your code on the Spark or cloud platform. Okay, go back to the project. First, I will introduce the motivation of this project. This project I want to answer a very simple question about where the mitosis is in the big medical image. So the right side shows a piece of the tissue image. This image is stained to highlight the cell structure, and it's placed under a microscope to be examined by the physician. So basically, physician want to count how many mitosis are there in this image, as this number will be a very strong indicator of the cancer. But there are a few challenges here. The first issue is about subjectivity. So normally the physician will get a very long time professional training and a hands-on experience. But the results still may be subjective, not very objective. So another thing that even for the experienced physician, it will be time consuming for them to count the mitosis from the input data. So here we want to build an algorithm to automatically detect the mitosis from the stained image. But when we build the model, we met a few challenges. The first one is about a large background area in the image, such as the white area here, and also the pink area that's about tissue fluid. And we only want to detect the black point in this image. And a very small number of mitosis compared to the normal nuclei there. Another issue about the limitation of the training data sets. So we couldn't find too many training data sets on the public. So here is an example of the mitosis. As you can see, in this whole image, we have more than 100 nuclei there, but only one point is the mitosis. So the data is really unbalanced there. And yeah. For the first, I will review the related work. Currently, there are 3 open challenges. They provide training data sets, such as Tuple 2016, and ICPR on 2012 and 14. And I will give a simple introduction about the data sets. For the Tupac 2016, they have about 600 whole slide image, and the data size about more than 600 gigabytes. But for the training label, they only have the label for about 50 gigabytes. So the training data set is very small. And for the image, they have different kind of resolutions, such as 2000 by 2000 and 5000 by 5000 here, and store them in the TIFF data format. And for the label, the physician labeled the center of the mitosis, so at a point with the x and y coordinates, and solve them in the CSV data format. And all the labels are examined by 2 people to keep the data quality, because sometimes the result may be subjective, right? So, okay. And there are some research. They published the papers, and for the machine learning-based approach, we can divide them into 2 categories. And the first one is a handcraft feature-based approach. Basically, people predefine the features such as the size, shape, texture as a feature, and build some classification models such as SVM or random forest, and get a classification result. And the second approach is the CNN-based approach. So they use a convolutional neural network to automatically generate the feature on multiple scale, and then make a classification based on these features. And for the CNN-based approach, we can also divide them into 2 kinds. The first one is classification-based. That one is we introduced last year, last April. And now there's another one is object-based approach. And I list 3 selected reference here. The first 2 is the classification-based approach. And the third one uses a faster RCN to do the object detection. And now, this time we introduce our new approach. This one is also object detection approach. The difference that I will introduce the details later. Okay. First, I will review the classification-based approach we introduced in the last year. So the first row shows data preprocessing, and the first image shows the original whole slide image, and the white area is the background. So, and the pink area is about the tissue. So as we can say, almost half of the real are the background, right? And the physician choose the high power fields from the whole slide image. Basically, this area are about the tissue. And the size is about 2000 by 2000 or 5657 by 5000. And this size is still too big for the deep learning model, so we split them into small tiles about 64 by 64. And the one issue is that there may be some mitosis on the edge of the tiles, so we add some overlap between the tiles. So the overlap is quite important because there are very small number of mitosis in the image, right? If you use a very big sliding step, then maybe you miss some mitosis on your training data sets. So we based on the training the tile, we train the VG model and the resident model. And once we get the model, we make the prediction here. And we add the data augmentation and marginalization to improve the inference accuracy. And once what are the mitosis original big whole slide image, and then we can get the final mitosis coordinates. There are a few issues, performance issue here. First one is about the background data, background area. So here we still input the background data into the as a training data set. So it will increase the training data set, but this kind of data set is not that useful for the model training because this is just the background, right? And also we'll make the model be complex because the model will identify whether the input tile is a background or foreground first, then to identify that is a mitosis or just a normal cells. And the second one is about what's the best sliding window step. So here, basically, we use a very small sliding step to try to get at to keep the mitosis in the training data set, but it will make the training data set too big. So if we do this step in the inference, so the inference time will be very long, yeah. And another issue is about the augmentation and the marginalization. Although it can improve the inference accuracy, but there are some performance issue when you do the inference. So we update our approach to propose a two-stage XM-based object detection model. Basically, the first stage, we use master RCN as a proposal model to propose the tiles. And based on the proposed tiles, we build a red-light-based classification model. Okay, and so the first master RCN based model can solve a few problems. The first one is that it will remove all the background in the training data sets. And also, for the tissue fluid between the cells, we can also remove this kind of area. So the training data can be removed, can be reduced a lot. Basically clean the training data, remove the background, and it will also make the classification model training be faster. So I will go to the details for each step. So the first step is about the data pre-process. This step is pretty simple. Basically, because the whole slide image is too big, about 50,000 by 50,000, too big to be held by the GPU, so we split them into 512 by 512 as a region of interest. And based on the region of interest, we directly input them into the master RCN model to do the nuclear segmentation. So this big figure shows the segmentation result. So the colorful polygon is the segmentation result. We only detect the nucleus and without any data in the background, such as the white area and the purple area here. And based on this polygon, we use the center of this polygon to generate the tiles. This tile will be the proposal for our second model. So here for the training or master RCN model, we use the data from the Kaggle Computation data science bowl, and they provide around 30,800 training enabled for the segmented nuclei image. And this data varied in the cell type, magnification, image modality, so they have good generality. So we can use the model on our tissue data sets. And for the model configuration, we use the Redlet 50 as a backbone and define different kind of stress size, anchor scale, and the ratio of the anchors. Basically, you want to detect the feature at a multiple scale and also detect different size of nuclei. And we use the master RCN code implemented by the Matterport, and we make a little revision to improve the performance. And this figure shows the architecture of the master RCN. Basically, it adds a mask layer to the faster RCN, so we can get the mask of the nuclei in the image. This slide shows a result from the master RCN model. Here, we combine the several tiles together as a big image, and we zoom in and we can see the color polygon, and we use the center point to generate the red box that will be the proposal tiles, and the green circle is the ground truth label. So once we get this kind of proposal tiles, we convert the problem to be a classification problem, whether this red box is contain a mitosis or not. Before we do the classification, we need to evaluate how many mitosis the proposed tile covered, and we use the Toolkit 2016 training data sets to evaluate, and the result is that almost 99% of the mitosis are covered in the proposal tiles. That's what we want, because we do not want to miss too many mitosis, because there are only small number of mitosis in the training data sets. And we also cluster the overlapped proposal tiles to further reduce the number of training data sets. approach comparison. Basically, here we compare the old approach and the new approach here. Here we use the AMOSN to generate the proposal. We do need to using the sliding window to generate the tiles, and it will remove all the background here, and no need considering the what's the best sliding step. And here is a number here, and we compare the training tiles between the old approach and the new approach. At the old approach, we have on the validation high power fields, we generate about around 3 million training tiles. However, once we use the new approach, we reduce the number to around 3,358,000 tiles. So about 9 times reduced, remove most of the unnecessary data, training data sets. And for the second stage, to build a classification model, it will be similar approach we introduced in the last year. Here, and the first step is the augmentation. We use random rotate the image, and also adjust the color, and change the contrast, and to add Lloyd to the training dataset, and inflate the dataset at the data size. And we use treat this problem as a binary classification problem, so we use the logistic loss as the loss function, and we record the loss value, F1 score, precision, and sensitive in as a matrix, and visualize them in the tender board. One big problem is that there are a lot of false positive cases when we finish the first round of training. So we use a model trained at the first round to generate the false positive case, and train the model again based on the false positive case to make our model get better performance on this kind of very hard non-mitosis case to reduce the false positive case. And after the classification, we need to do some post-processing. Basically, so here, for each identified mitosis, they may be very close. And when we compute the F1 score, the challenge defines that if the mitosis are very close inside of 30 pixels, they will treat this one as the same mitosis for the true positive case. But for the false positive case, they will treat them as a different mitosis. That will impact the F1 score a lot. So we use the dbScan to cluster the classification results. Even though we have the master RCN to remove the background and clean up the training data sets, and it's still time consuming to run the inference on the large volume of data sets, because 600 gigabytes, the small data sets. So we try to run Spark with TensorFlow together to do the inference. First thing that we develop a very simple GPU resource manager, and this manager can figure out how many GPU resources are available on each GPU load in the Spark cluster. And based on this cluster, based on the available information of the GPU, and we will launch each RDD partition for each GPU. And inside the partition, we will TensorFlow or server to load the master assistant model and the classification model, and run the inference on the data sets, and do the data processing such as data generate the ROI tiled augmentation, and stack the result together as a final result. And the inference result, so between these two approaches, currently F1 score is similar. Our new approach is a little bit better, but it's still ongoing. But one big improvement about the inference time. Before we need around 9 hours. Now we reduce time from the 9 hours to just 1 hour and 11 minutes. That's because we remove a lot of background data and no need considering the sliding window step, because before we use a very small sliding step. And another big thing is that we do not need the data augmentation and the marginalization in the inference. So that saves a lot of inference time. This project is a part of the model asset exchange project. So main project is to develop, wrap, and share the open source deep learning model with pre-trained weights. And we wrap them as a REST API and store them in the Docker image. So it will be very easy for any user to use the deep learning models. And I will show a live demo here. We published the classification model in our Max project and share the weights and code on our GitHub. And I will show how to use this Max model. So basically, the first, you can grab the Docker image from the Docker Hub just by this one command. Then it will run the REST service. Or you can download the code from the GitHub and run the Docker on your local laptop. And I just run it on my local laptop here. So I already downloaded the code. We can build the image. Oh, sorry. I already built it, so I directly run it now. Then I can access the service on my browser. So this just provides a REST API, and you can try the post, try it out, and upload the data you want to test. And here is a simple example image here. And you run it, then it can return the prediction probability. For this one, it's about 98% potable. So that means this one is mitosis. You can also try another image. Yeah, this one is not. And it's pretty quick. Just if you want to use the model, then you can just call this REST API. And we also provide a workflow engine. You can chain several math models together as a workflow. Just drag and drop the model button on your browser and chain them together as a workflow, and run several models together. And if you are interested you can go to our GitHub here and to find our project. Okay, thank you. So this is the link for our project and the link for our IBM project. Any question?
Sorry, what?
You mean, so vector-based and pixel-based, right? So now we only use the same model to do the training on the pixel-based, and we didn't use any such as traditional method to do the build the feature vector. So we didn't do that kind of comparison. Yeah. Yeah. Sorry, I don't have. Yeah. Sorry. You mean the different kinds of scale? Could you use the?
Have you guys tried using grayscale testing to weed out a lot of the false positives?
You mean change the image color to the gray or what? So on the nuclei data set, they include from the Kaggle data set, the big sample, they have different kind of color, green, gray, or colorful data sets. But for the method data set, all of the data set are colorful. So we didn't do the gray test. But when in the data augmentation, we change the color to the gray and also the colorful. Yeah.
And how do you make sure that the color is exactly the same if when you transfer? So, for example, are you using a CMYK scale?
So I think we want the model to be robust to handle this kind of data with different color, right? Even different resolution, right? That's what our goal, right?
Is that implemented though?
So I think the CNN model can handle that because the feature they detect is at a multiple scale, right?
Okay. Cool.
Mm.
Thanks.
So just a quick question. The data set that you guys are using, this was part of the Mikai competition way back in 2013 or so. So how does your results compare to the best results at the time with the competitors?
So the competition is still open. You can submit the result for the post competition. Last year, when we submit the result, we ranked the third position. But in this year, there are two teams submit the results, but our results still top 5.
They were what? I'm sorry?
Still ranked top 5.
Oh, top 5. Okay.
Yeah. But we still training the model, hope that our new project will get a better result. Yeah.
Okay, thank you.
Okay, well, let's thank our speaker again. And that's it. Thanks again for App Dynamics, and we'll see you next time.